Good morning. Thank you for being here. Today we have a talk which I think is very interesting. I'm very happy to introduce to you Sergio Martínez González. Sergio, he comes from Mexico. He works at the INAOE, Instituto Nacional de Astrofísica, Electrónica y Óptica y Electrónica, en Puebla. He's an expert, he's a theoretician. For some reason, I don't quite understand. He likes to work with observers as well. So he's a theoretician who likes to see whether or not his predictions work. And he's an expert in the hydrodynamic of the stars, massive stars, in cluster of starbursts in galaxies, right? He started doing very detailed simulations in the nearby universe. He's able to simulate whatever outbursts, whatever evolution of a supernova, a starburst in the spiral arms of a galaxy. And more, he becomes interested in also understanding what happened with starbursts at a higher set. Why? Because they are objects which are quite intriguing. And he has come with some solutions to understanding some of these phenomena, which seem to be a bit difficult to see how they happen. He's also an expert in dust production and dust destruction, which, as you all know, comes from supernovae. So today he's going to give us a more like general talk, getting to a very important result that he had got regarding the case of the so-called blue monsters galaxies, that he will tell us more. Also, for you to know, he's here invited by Fundación Occidente. He will be with us until the middle of May. He will be more than happy than iterate with any of you if you consider he can help you. And I think that's all I want to say. Just again, saying, Sergio, thank you for coming. Thank you for your work. And I hope we are going to enjoy with you, I'm sure. Thank you.
Gracias, Cristina. Thank you. And thank you to Fundación Occidente for sponsoring my visit to the Instituto de Astrofísica de Canarias. I am enjoying a lot this visit. So I will speak today about those produced by supernovae in different environments, a little bit far from classical interpretations that supernova explosions destroy all the dust in their surroundings. And then we are going far to the very high redshift galaxies. So I've been working with Casiana for a long time. The first time I came here was 2014 for an Estallidos meeting. And now I'm enjoying coming back. So there is evidence in the early universe that there are galaxies at redshifts higher than 8 that already contain lots of dust, millions of masses of dust, after these galaxies are only few 100 million years of evolution. So this is fascinating, this is intriguing, and this is showing that dust production starts very early after the formation of the first stars and the first galaxies. So there are galaxies at redshifts 8 showing these millions of solar masses of dust being produced, but also results in the last few weeks, there is evidence of dust production and in massive quantities at redshifts more than 11, which is very, very interesting. There are many examples of this. I will not speak about all these examples, but with ALMA, with JWST, and many other observational facilities, we have this excellent evidence that this is already occurring very early in evolution of galaxies. So the question is, what is the origin of this dust? So, for example, in the Milky Way, we can think about AGB stars. They can produce up to 10 to the -4 solar masses per one of these stars at this stage, and they are a lot. So they contribute a lot in the Milky Way to the dust budget. But in these high redshift galaxies, the times involved are not enough for allowing these stars, these low mass stars, to start creating this dust. So they start creating some dust, a little bit of dust, starting from 500 million years in evolution. So this is these galaxies I was speaking before, these are younger than that. So, and they will start contributing in large numbers after a giga-year of evolution. So it is difficult to reconcile dust production by AGB stars with dust production in these galaxies. So the other alternative is that we can grow those grains in dense molecular clouds in order to explain the large mass of dust in many astrophysical environments. But for that, you need to have some dust first. So this is not to explain dust production, but to increase the dust mass. And there are objections about grain growth in high redshift environments because, for example, the CMB temperature is very large, and this affects the sticky probabilities onto dust grains. So for this, you need to accrete some dust species onto the dust grain surfaces, and this is more difficult as the dust grains are warmer and they are affected by the CMB. So I will not speak today about this alternative, but we proposed in 2021 the only explanation for this in supershells. So in starburst regions, I think it is possible to overcome all. There is a list of objections by Andrea Ferrara published in 2016. And we went one by one, and the only environment that we can propose is can increase their mass in supershells. Other than low mass stars, we can think about massive stars. They can produce lots of dust in eruptions, after stellar eruptions, and other processes like stellar mergers, direct collapse instead of a supernova explosion. The star collapses directly to form a black hole, but not all of the mass is incorporated into the black hole. So a little bit of mass is ejected, and this is also a good place for dust production. It is not investigated a lot in the literature right now, how much, but it is interesting to think about them. And also, of course, binary interactions involving carbon-rich Wolf-Rayet stars. So in the winds, it is possible. The number is like 10 to the -7 solar masses per year, but over a short period in evolution for these massive stars that go to this phase. And of course, Colloquium supernovae. So in nearby Colloquium supernovae, there are supernova remnants. There is evidence of massive dust production. So, for example, this supernova remnant 1987A showing production of solar mass of dust just a few years after the explosion. So in the first production starting after 1,000 days following the explosion. And Cassiopeia A also showing roughly 1 solar mass of dust produced in this environment. There are many examples in the literature right now, even with those masses larger than the ones I just mentioned. But it is pretty clear that the ejecta of core collapse supernovae are the appropriate sites for dust formation because they contain the appropriate elements for condensation. When we have the explosion, the ejecta is hot, but with expansion it cools down and is still pretty dense. So collisions and sticking of different species can happen in these environments because low temperature, high density, and the availability of refractory elements or oxygen, carbon, and many ingredients. So it is just natural to think about dust production in those places. It was proposed, I think, more than 70 years ago or 60 years ago. So it was confirmed just about 15 years ago. But the common belief in the literature is that supernovae may destroy more dust than the amount they produce. I just mentioned that they can produce solar mass of dust roughly. But for example, there is a paper by McKee in 1989 mentioning that single supernova explosion can destroy 70 solar masses of dust. So a lot. And this is because one usually can think about driving of shocks by supernovae, and they are collecting the interstellar matter, including dust, and so a thin, hot shell. And within this shell, we can have lots of collisions with ions and with gas particles that can trigger the ejection of individual atoms from the surfaces of dust grains, and even completely or fully destroying the dust grains. So this is the typical picture of that. But not only that, this same shell with time collects a lot of mass and a lot of pressure. And with this pressure, in order to balance again or to equilibrate the pressures for the supernova remnant, one has to, or the supernova has to drive another shock, but this time not collecting the mass of the interstellar medium, but processing the supernova ejecta. So it is propagating at the very site of dust formation. So a very powerful shock that may destroy the dust that was just recently produced. So it is not looking good for the survival of dust grains, either persistent or in the supernova ejecta, the fresh dust that was just produced. So there is an intense debate in the literature about that, many papers, many groups. So a few years ago, or some years ago, we were thinking that we have the tools to investigate this problem in detail with the hydrodynamical simulations and analytical results that we can provide. So we have carried out tons of hydrodynamical simulations with flash code, in which we can inject stellar winds, stellar eruptions. We can follow the injection of supernova shocks, supernova explosions, not one, but as many as we wish, and other ingredients like turbulence, gravity, and cooling, which is super relevant for this problem, and naturally follow the formation of the shocks and instabilities, which are also important. So for this example, this is a simulation of a recurrent nova. So in this case, I model 9 eruption events. So we have this structure of nested shells. So this is one of the examples. This is not published yet. This was submitted. The talk is not about nova eruptions, but just for reference. And I also developed a module for this flash code, which is called Cinder. And we have to assume the existence of some arbitrary grain size distribution. So we are sampling the different grain sizes. And we can follow on the fly the destruction of dust grains. They can grow in low temperature environments. And very important to follow gas grain collisions, which can trigger a lot of cooling. The thermodynamics of the supernova remnants can be even be controlled by gas grain collisions. Cooling is so part of the kinetic energy, which is transferred after the collision, is immediately radiated away by the dust grains. They are very efficient in radiating energy. So at gas temperatures of larger than 10 to the 6 Kelvin, a million Kelvin, the most important process for cooling is gas grain collisions. Of course, if we have dust grains, which are destroyed at the same temperatures. So it is very important to follow this balance, destruction and cooling at the same time. That's why it is needed to do it on the fly. There are other processes which are not included in this Cinder module, but I will speak also about getting an idea of their importance with post-processing, which I have done also. So the first thing to check is the classical example, the example that you can find in textbooks about the evolution of supernova remnants in uniform media. So this is like the common idea. So we have supernova explosion at this uniform medium. So here we have density. On the right we have temperature. We have here the dust to gas mass ratio. This is dust that was produced with the explosion, which is assumed It is not calculated self-consistently. But in this simulation, I assume half solar mass of dust being created. And this is velocity, radial velocity. So we can see the driving of the forward shock and then the reverse shock, which is propagating into the ejecta, destroying some amount of dust. You can see it here again. So this is the very famous reverse shock that it is mentioned a lot, but it is not always shown like in this movie. So after that, we can measure from the simulation the amount of dust that is preserved, the dust that was injected with the ejecta, but also dust that is being destroyed in the surrounding medium. So this is the dust mass. This is the time after the explosion, and this line corresponds to the initial, this blue line, to the initial amount of dust in the ejecta, and we can follow the destruction. So it is slowly decreasing this curve, but also measuring the amount of dust that is being destroyed in the surroundings. And very easily, this amount of dust destroyed in the surroundings is by far more important than the amount of dust that was produced and is surviving at this stage very rapidly, just 6,000 years after the explosion. But we also tried not only this low density medium, this is 1 particle per cubic centimeter, but also 1,000 particles per cubic centimeter, which is also worth testing. In this case, dust destruction was happening very fast, not even 1,000 years after the explosion. We destroyed everything in all the dust in the supernova ejecta. But we can see an interesting result, that dust destruction in the surroundings, about the ambient dust grains, is not continuing forever. So we have this stabilizing very, very rapidly. And this is because of radiative cooling. So the shell that was of gas that is collected by the forward shock is very hot in the beginning, but it is very dense, and radiative cooling scales with the square of density. So very rapidly, this shell is not very, very hot, but it can be at temperatures lower than 10 to the 5 or 10 to the 4 Kelvin. And these temperatures are very safe for dust survival. So this is interesting to check at different densities. But still, we can think that common belief in the literature is right, that dust destruction is more important than dust production and survival of dust in supernova ejecta. But the first thing to think about is that the ambient ISM is not uniform, it is not homogeneous. We can think that we have to consider that there is stellar evolution before the explosion, and with this, the release of stellar wind, and the stellar wind just does the same to the ISM. The ISM is collected into a thin shell, but this time not very hot. It is massive, and it is surrounding the massive star. And we have to consider this evacuation of the surrounding medium and the formation of a shell of interstellar matter. So this was not done, surprisingly, until we did it. So this is just the example. This is the release of the stellar wind for some millions of years. And later we will see the supernova explosion at the center here. This is the evacuation of gas, so densities here are very low, and in the shell are very large. So what we can see is that the forward shock is unable to be transmitted a long distance into the shell. It is basically stopped. Some part of it is reflected, but it is not as the classical supernova explosion. Actually, in these cases, we don't recover the set of Taylor solution, for example. It is not realistic. So the share of kinetic energy, thermal energy, and radiated energy are not the ones predicted by the adiabatic model of set of Taylor, in which there are no radiation losses. So we have this, the supernova ejecta is evolving within this low density cavity. And because it is low density, we don't have many collisions, many gas grain collisions here. So this is good for the survival of dust grains produced after the explosion. Basically, nothing is being destroyed in this cavity because densities are like 10 to the minus 2 particles per cubic centimeter. But on the other side, in the shell we have the mass of interstellar dust that was collected, and given the fact that the forward shock is unable to process a large mass in this shell because radiative cooling steals the energy. So we have lots of radiation here being released, and most of the dust grains in the surroundings are unaware of this shock, so they are not destroyed in large numbers as in the previous case of uniform medium. So this is what I just said, that the excavation of this cavity changes everything. So we have a transmitted forward shock that moves into the shell, but it is almost impossible to run the full shell. And the reflected shock that moves into the ejecta. We no longer think about just the reverse shock, but a reflection of the forward shock. So we can think again about this same plot, this post-explosion time, the dust mass, and the dust mass that was injected with the simulation, half solar mass, and you can see that dust destruction in the ejecta is almost or negligible, basically. A little bit of it is being destroyed, but basically it remains the same amount, and dust destruction in the ambient medium. So in the beginning, there is no destruction until we reach, or we have the collision of the forward shock with the shell after 3,000 years in this case, and we can see some destruction, but not growing a lot. So in this case, we preserve more dust produced in the ejecta than the amount that is being destroyed in the surroundings. So this is changing the original picture of that supernovae destroy more dust than what they are able to inject to the interstellar medium. This is 1 particle per cubic centimeter in the surrounding medium. This is again 1,000 particles per cubic centimeter. We recover the same result. They are not so different in this case. In the previous case of uniform media, there were differences, as I mentioned, but in this case, again, dust production is and survival is winning this battle. So we were asked several times about not including other physical processes for destruction. We were including thermal sputtering just because of the high temperature of this gas. We can trigger collisions, but there are other mechanisms, and we tested all of them in the same environment, this low density cavity excavated by the stellar wind. So we have mechanical torque disruption, kinetic sputtering, grain shattering, and other processes, and all of them show to be very inefficient within the low density cavity. So for these processes, we need some relative velocity between the non-thermal relative velocity between the kinetic, between the dust grains and the gas particles, and even assuming super large velocity difference, like 500 kilometers per second or more than that, these processes are not very important because low density, so encounters are not very common. So the result is still convincing after considering all the processes that are mentioned in the literature to be very important. And also last year I published this letter showing that if the ejecta is clumpy, and these clumps already contain some dust, and the shock, the reverse shock is propagating into these clumps. If the clumps are dusty, radiative cooling is also very important within these individual clumps. And with that, not only we protect the dust grains in clumps, but also the mass of these clumps can grow. So they can become more massive. Instead of the reverse shock triggering the destruction of dust grains, the reverse shock is triggering the enhancement or the increase in the dust mass. So I explore this large parameter space for different dust to gas mass ratios from 0 dust to 10 to the minus 2. So this is one gram of dust per gram of per 100 grams of gas. So the story is not so easy if we consider radiated cooling and excavation by stellar winds. And also we were thinking about stellar eruptions because prior to the final supernova explosion, we can have the release of massive amounts of matter by the progenitor star. And it is shown also in the literature, for example, in Eta Carinae, that there is a shell, a bipolar shell produced by different eruptions in the 19th century. And with that, there was dust production in these shells. So basically, or very similar to the production in supernova ejecta, we have production in eruption ejecta. But we can think that these shells are not very far from the explosion site, and one naively would think that they will be completely erased after the final supernova explosion. So this example, we have the bipolar. Before the explosion, we have the bipolar shell that was produced after a stellar eruption and the collision with the forward shock. So processing this shell, imagine this is the shell in the famous Eta Carinae nebula, and we have the collision with the subsequent forward shock after the supernova explosion. And the result for this, we tried several cases of different ejecta masses, different energies, and different intervals between the final eruption and the last eruption and the supernova explosion. So it is shown in the literature again that eruptions can happen centuries before the explosion or just a few months or few weeks after the final supernova explosion. So these gaps, these time intervals are very important for the survival of the dust grains in the erupted shell. But the main thing is that we can convert as much as 50% of the energy that was released with the supernova explosion just by the collision with the eruption shell. So this translates immediately into weaker forward shocks, the ones that are responsible for destroying dust grains not only in the erupted shell but in the larger interstellar medium. And with this consideration, we can preserve as much as 75% of the dust mass that was produced after the stellar eruption. So this was this was contrary to expectations because the spatial scales here are very, very small. So this is to this size it is 0.1 parsecs. So this is very close to the progenitor star, and this dust also is also surviving the final supernova explosion. So we have tried many examples for different ambient media for individual supernova explosions, but I like star clusters, superstar clusters in particular. And there was also a common belief in the literature saying that cluster core collapse supernovae do not significantly contribute to the dust injection rate, since any subsequent supernova will destroy the dust produced by the previous one. So this is easy to understand that we have many supernova explosions happening basically at the same place and destroying the little amount of dust that was surviving after the first supernova explosion, then a second, and many more. But we tried also because we had the tools for superstar clusters. So in the beginning, there was this superstar cluster wind. So all this medium in blue colors. Again, density. This is again temperature, and this is the dust to gas mass ratio. So one had to consider that there is a volume in which the massive stars live. So there is a stellar density distribution, a gas density distribution for the star cluster wind, and not all supernovae or supernova remnants expand in the same direction. They have a preferential direction for expansion, and it is not guaranteed that a subsequent supernova explosion will be interacting a lot with the previous supernova remnants that are expanding in a completely different direction. They can, just by chance, they can explode in the same direction for one or two examples. But if we consider stochastic explosions or mass aggregation in this cluster, so the end result is that they expand in different directions. And with this, it is relevant to understand that we will have some dose injection, some time of destruction, then the next supernova explosion, and we will be here seeing these peaks: injection, destruction, injection, destruction. This is the most violent environment that we can think of. So imagine thousands of massive stars. This cluster is 1 million solar mass in stellar mass. So we have thousands of supernova explosions and thousands of dust masses being injected after each one of them, and we have destruction. In the end, we have like 15 or 20% of dust produced after this starburst event. Then we consider not only this case in which there is the star cluster wind, but the bubble that is created around the individual superstar cluster. So for that, we consider a clumpy low metallicity molecular cloud. So in the beginning, we have this cloud, and then the release of the star cluster wind that is formed after the collision of individual stellar winds. And we have gravity here playing a role, grain growth in these clumps. And in the center, with stellar evolution, we are following stellar evolution also. After the first supernova explosion, we have the injection of dust by each supernova ejecta. And we see here how dust is being injected into the, again, this is a low density cavity being formed because of the interaction of the stellar or the star cluster wind with the molecular cloud. And we are excavating again a cavity. So in this case, we try 236 supernova explosions. So a few million years of evolution. And again, we recovered this result that dust is the dust mass is increasing with time, despite the fact that some part is being destroyed. So this was done for individual molecular cloud, individual superstar cluster. But then we can extrapolate the results. And the prediction in this model is that for a galaxy of the same stellar mass as this example that I mentioned in the beginning of the talk, we can lead to the preservation of a few million solar masses of dust, which is very compatible with these observational estimates for this object, which is at redshift 8.3. So we are very close to we are in the middle of these two derivations. So millions of solar masses of dust being produced after this era of supernova explosions and evolution of superstar cluster. So this is a success in the model. So for that, we have already modeled the fate of dust grains, not from one source, but from some dust that is persistent, and it is protected by the presence of the shell that is produced or formed after the stellar wind injection in individual cases or in superstar clusters, but also circumstellar dust grains, the ones that are produced after stellar eruptions. And in these cases, we can expect the weakening of the forward and reverse shocks. So this result was important not only to preserve the dust grains that were produced after the eruptions, but also these shocks will be propagating to the larger shell. The stellar wind is operating for millions of years, so there is a small shell after the eruption, but a very large shell or a bubble that is formed because of the interaction of the stellar wind with the interstellar medium. And by the time of collision, we will be having a very weak forward shock. So this is also important for the preservation of pre-existent dust grains, and also ejecta condensed dust grains, because the supernova ejecta or the remnant expands within a low density cavity. We don't have many collisions, so this is good for survival of dust grains in the ejecta. So these three types. Okay, so we have some success in explaining why galaxies are dusty at these redshifts 8, for example. We have numbers comparable to the ones derived in the literature. But surprisingly, there are galaxies at redshifts higher than 10. These galaxies already contain the order of 10 to the 9 solar masses of dust. So they are forming stars very efficiently. And the metallicities of these objects are not so low. So they have like 0.1 the value of or the solar value. So 0.1 in solar metallicity. So by that metallicity, we can expect that some dust should have been produced. And these galaxies are very compact, and the standard dust enrichment scenarios argue that we can expect a dust to stellar mass ratio 10 to the minus 4. So for these galaxies, 10 to the minus 2. This is the scenario for dust production in a galaxy, considering all destruction processes. So based on our estimates or on our own estimates by the group of Ferrara, they took these numbers, and the number is that for this galaxy, 10 to the 9 solar masses of stars, we will expect like 10 to the 7 solar masses of dust. But it is not the case. These galaxies are very, very UV bright. They are transparent, almost no dust attenuation. So the number is 10 to the minus 4. So for this galaxy or these galaxies, we will expect 10 to the 5 solar masses of dust, which is not there. So the interpretation can be that dust production is not happening despite the metallicity, which is very difficult, or that dust destruction is very efficient in this type of objects. But we were considering with Cassiana a different scenario, because these galaxies are very compact, and we can consider a scenario like this galaxy, and similarly to the supernova explosions, expanding in a preferential direction, because the remnants fill the density gradients. So again, here, if we have this configuration, not the individual supernova explosions, but the super bubble that is created by the star cluster winds and supernova explosions can take or can open this channel into the galactic halo. And with that, we can separate the location of the stars and the dust grains, which will be discharged into the ambient or into the galactic halo. So considering that, we have also experienced in this so-called blowout. If we can retain these dust grains inside the galaxy, it is good for star formation. We can see the positive feedback scenario in which we can recycle the gas and the dust grains from previous star formation events, and this is good for star formation. But if we release this dust and discharge this dust to the halo, so this will be a different regime, not a positive feedback regime. And we can take the numbers we just derived from 3D hydrosimulations, and we can predict this 10 to the minus 3 or 10 to the minus. I went to the lower limit, but this can be 10 to the minus 2 also. So considering 10 to the minus 3 in this fraction of dust mass versus the stellar mass, And then we have some scalings that were produced by Santiago Jimenez, our collaborator. He performed thousands of hydrosimulations for this type of configuration, some disk and some bubbles expanding into this disk. And according to the location or the altitude within the disk, we can, or the height, we can see different shapes of super bubbles. So in this example, this was just at the galactic plane, exactly at the center, and we see this bipolar shape. But if the star cluster is located up or down the galactic plane, so we will see expansion in just one direction, preferentially. So with this, we use this. These are also 3D hydrosimulations, but in a simplified scheme. So this allows to perform many more simulations. And with that, we can predict that less compact, lower mass clouds containing a star cluster lose more dust because their potential, their gravitational potentials are less important. And we can have this supernova blowout, so this release of gas and dust to the galactic halo because of also development of Rayleigh-Taylor instabilities, and in this case it is more efficient, this release. So we explored this parameter space because we have all the relations needed for this large exploration for different cases of the star formation efficiency, so 0.1 and 0.5, but it can be larger than that at the scale of superstar clusters and individual molecular clouds. And in this plot we have the stellar mass versus the core radius in the star cluster, in the star cluster. So the compacity or compactness matters a lot for this, and also the gravitational potential well of the superstar cluster. So very massive superstar clusters can retain a lot of dust. This release of gas and dust is not happening. So in these cases, we can anticipate the positive feedback scenario, triggering more star formation within the same region. But for lower mass star clusters, it is easier to release, not to retain the dust at the cluster scale. So we can we can average a cluster, a population of superstar clusters for the whole galaxy. And also it is mentioned, or it is inferred in the literature, that the fraction of stars that belong to bound clusters is close to 100% at this redshift. So basically all stars belong to star clusters, bound star clusters, or a large fraction. So with that, we have to consider the cluster mass function, some distribution of star cluster core radius, and with that we can produce this synthetic galaxy and consider the blowout lowering the dust budget in a galaxy like the one I was referring, very compact, and with this population of star clusters, and we can decrease the amount of dust by 1 or 2 orders of magnitude, which is or it is compatible to the observations of these blue monsters. I forgot to mention that these systems, these very compact, very high redshift dust-free systems are called blue monsters because they are very UV bright. They have this young population of stars. And we are in the same regime for this observation. So we can naturally explain without assuming anything exotic, like or not exotic, but we have standard IMF, standard cluster mass function, standard sizes for star clusters, etc. We are not assuming top-heavy IMF or anything like that. And we can reproduce the dust to stellar gas, the dust to stellar mass ratio, this 10⁻⁴ that is reported for these blue monsters. So it is not only that we are not destroying all the dust within the star cluster or star forming regions, but also we can release this dust to the halo because of these galaxies are very compact. So they are safe for some time outside of the galaxy. So we have, I am just finishing that explore the case of individual core-collapse supernovae, and with all these considerations of the stellar wind, the formation of the super bubble or the individual bubble with the cavity in the shell, we can see that individual core-collapse supernovae contribute more dust to the interstellar medium than the amount they destroy. But this is also true for core-collapse supernovae, and also we tested pair instability supernovae, which are not proved to be efficient dust producers, but there is indication that they might be if they are like established. If there are established observations of pair instability supernovae, we will know about that in the future. But in any case, we are predicting that they inject more dust to the ISN than the amount they produce. And also, we have shown that with analytical scalings, that we can also reproduce these galaxies, not only the dusty galaxies, but the galaxies that are very compact and they are UV bright. And we are naturally reaching this regime of retention and comparison with the dust mass to the stellar mass. So we have connected not only dust destruction, but also redistribution of dust within structure multi-phase interstellar medium. And I am finishing just now. Thank you.
Thank you, Sergio. Thank you very much. Very, very instructive talk. So now it's time for questions. Do you have any?
So in this blowout scenario, you say that part of the dust ends up in the circumgalactic medium, intergalactic medium, or something like that. And the question is whether there is observational evidence for this dust outside galaxies very early on.
Outside galaxies, yes. There are studies in the, or even, well, I am more familiar with the theoretical side, and it is the intergalactic medium contains, it is very hot, it is in clusters of galaxies, and it is considered that there is dust there. I'm not sure if this is proven or not, but it is expected that there is dust in the surroundings of galaxies.
But the question was about these very, primitive galaxies at redshift 10. So is there any evidence of dust in this early universe?
No. It is not observed at this point because, well, once you are leaving the galaxy and you are not together with the stars, it is very difficult to observe these dust grains because they are not exposed to the radiation field or to the collisions. It might be possible, but at this point, it is not the case that we can observe this dust.
Okay, thank you.
But it is a good idea to test if there is some chance. I will be happy to discuss with observers if it's possible or not.
Okay.
Hello, thank you. You mentioned that bursts are stochastic in direction, and I wanted to know if by stochastic you mean uniform in direction, or there is some correlation with respect to past directions of past bursts.
Okay, what I was assuming that there is a stellar density gradient inside the superstar cluster. So we were trying different locations. First, we were placing them at the center, and we can see that the expansion is roughly spherical, but then trying in the periphery of the star cluster, and we can see that it is growing. Then we were sampling stochastically from the same stellar density distribution And then we changed this and tried the massive stars more concentrated to the center, like to segregation, and with all these considerations. But we were not like it was just pseudo randomly in this process. So this is the way we did it. Okay.
Yep.
But we were not following individual like zinc particles, following stellar evolution and M-body interactions and all of that. So we were not. But right now we can do that also. So we are working on simulations. Actually, I didn't mention, but we are working right now on simulating a full blue monster galaxy, and we have some good results at this point for future.
Thank you.
More questions? More questions?
Hi, very nice talk. I had two questions. Actually, one of them is following up on what Jorge was asking before. Like with this blowout of the dust for galaxies at redshift 10 or more, I was curious if you know how frequent or how likely are these processes to happen? Because I imagine, as you saw before, at redshift around 8 or 8 point something, you have a complete different situation where your galaxy has a much higher dust, at least detected. While in this case, at redshift 10, that is just a few mega years earlier, you have a scenario in which the dust is completely blow out. So I don't know if, I mean, how frequent the conditions of the ISM of these galaxies you expect that these scenarios happening in contrast with at a bit lower redshift.
The answer is that we expect galaxies to be very compact at these redshifts, but the real answer is that we don't know because we don't have good statistics for these blue monsters. So we have like 15 examples at this stage. So they might be common because it is expected that they are very compact, and these galaxies are still building themselves, so they cannot be very large. And just naturally, you have just formation of the first star clusters in a galaxy. It is very difficult to retain the dust mass. So it should be pretty common, with the caution that there are a few examples in released in the literature. So
okay. And if I may, yeah, I think around slide 21 or 22, you have this comparison with the dust produced by the, yeah, here, I think the previous one.
Here?
Yeah, no, the one with the dust mass.
Okay.
With the numbers here. So basically those were the estimates based on what was measured in the observational studies and what you predicted of dust produced by supernovae.
Yes.
But this scenario of supernovae producing more dust that is destroyed is kind of, I mean, new or going against the current. So I wonder if there are other channels to produce more dust that could put your prediction a bit off. Like, because basically you achieve 100% of the observed dust just with the supernovae production. So there are alternative channels to consider in this epoch.
Yes, well, at this stage, only the massive stars at redshift 8, only massive stars with eruptions possibly, and with supernova explosion. But also in this simulation, we included grain growth also. So some part of this estimate is not only, it is not, no, it is not included in this number. Okay. But we can increase this by the grain growth, and in this simulation it is computed. And for example, in this individual molecular cloud, there was an increase of 200 solar masses of dust in the clumps. But you need some dust in the clumps. So that's why it is not included in this number, because we were considering, or we were thinking about the first dust grains in these galaxies. But it is if there is already a population of dust grains within these clumps, it is included in the simulation.
Okay, thank you very much.
Thank you. More questions? No more questions? Well, in any case, now, as you know, we have coffee at the cafeteria, and then there you can ask him more private questions of your particular topics. All right? So let's go for that. Thank you, Sergio.